now use this, sorry, let's pick a model. We could pick really any one we want, but in order for the simplicity to be good enough for lecture, let's just use this model here, the Prandtl-Taylor model. So the Prandtl-Taylor says in the region 0 to 11.5, we have this eddy diffusivity that's 0, and then it becomes a linear equation. So if I plot out what this actually looks like, this Prandtl-Taylor model, might guess, but just to give us a clear picture, we would have on this axis, let's plot epsilon m divided by nu. And then on this axis, let's plot as a function of, let's say, y plus. So as I move out from the surface, right, on the horizontal axis, I'm moving away from the surface vertically. We would see, I'll draw it in red, we would see, starting off, we have 0. And so from 0 to y plus is equal to 11.5, we have 0. Epsilon m over nu is 0. Then at that point, we transition to this different model where we have a linear increase in the eddy diffusivity. So that becomes here. So we kind of immediately jump up and increase linearly with position y. And the rate of increase is given by this, it's given by kappa, so we'll just draw it. So kappa, I don't know how to draw kappa, we'll just draw k. So k, kappa, y plus, right, minus 1. That's our equation for that region up there. Over here, this is what? So this is going to be kappa at 11.5 minus 1, right? This value here. And then the other thing to point out is this kappa is actually equal to a fixed constant. So this is 0.41. This is called the von Karman constant, VONKARMAN, von Karman. All right, so the von Karman constant is something that's been derived, that empirically has been derived to say this is basically the rate at which your eddy diffusivity is changing as a function of inner coordinate. And it's used in different models. You see it up here in this table. You can see that that same constant appears in a bunch of different models. Yeah. Yeah. Yep. So it's used, for a variety of situations. Okay, so let's take this this model that we are assuming, right? This is just something that we're saying is good enough for our purposes to solve for a velocity profile. And let's actually try to do that. So if we take the first part of this Prandtl-Taylor model where epsilon m over nu is equal to 0, and we substitute that into our differential equation here, right? We substitute in here for y plus less than 11.5, we're going to have what? 1 is equal to 1 plus 0 times du dy. So that's just 1 is equal to du plus dy plus, which is another way of saying u plus is equal to y plus in this region. So that really simple equation there is our velocity distribution. As you move positive y 1 unit, you get 1 additional unit of u, right? In terms of the inner coordinates. So that's just a linear increase. And if we look back at our plot up here, that makes sense. In this region here, we are saying that there's a 1-to-1 relationship between velocity and inner position, right? That's what that's saying. Okay, so that's the first part. Let's do the second part for y plus is greater than, say greater than or equal to 11.5. Let's substitute back. Now we have kappa times y plus minus 1. We have to substitute in, so that becomes 1 is equal to 1 plus kappa y plus minus 1 times du plus dy plus. So simplify that out, and that becomes what? Du plus dy plus is equal to 1 over kappa y plus. 1 and 1 go away. And then that's saying, solve for that, we end up with du plus is equal to dy plus over kappa y plus. Right? Solve or separate for u and y. Right, so that gives us a relationship for the velocity profile here. We can now integrate this. So integrate these two things. So we'll integrate with the left-hand side is where is this model going to be valid? We have to integrate, think about our integral. We want to do a definite integral. Where is the left-hand side going to be valid for u? Well, it has to be between our 11.5 cutoff and as you keep going, right? So we're going to integrate the left-hand side from 11.5 up to u plus, wherever we decide that is. And then on the right-hand side, we're also doing the integral from y equals 11.5 up to y plus. Why 11.5 on both? Well, because u plus is equal to y plus. So they're both 11.5. Okay, so we do that integral and we are left with what? So we're left with, see, u plus minus 11.5 is equal to 1 over kappa ln of y plus minus ln of 11.5. Okay, so we can just do some algebra there and we end up with u plus is equal to 2.44 log of y plus plus, let's see, ln of 11.5 plus 11.5 is 5.54. Okay, so now this actually looks like a velocity distribution. This is our velocity distribution in that region beyond that cutoff of 11.5. So, okay, let's look here. We have two things describing our velocity profile. One is going to be linear. Then you transition to something that's logarithmic. And that kind of makes sense, right? If you look back at our velocity profiles. Let's see. So yeah, this table now down here just shows you what we just did. We went through the steps and came up with our velocity profile for the Prandtl-Taylor model. You see it right there. Hopefully it matches. If you were to do the same thing for the different, for the other models that we had, you would get the equations that are given here. So you can see that there's, here we have two regions, one here, one region here, one region here, and then another region here. In this model, you have three regions where you're trying to deal with this stuff. And let's look at the, let's see, I think it's on the next page here. Yeah, so let's look at the plot of velocity. Inner velocity is a function of inner position. So this is a different way of looking at it. We're looking at the log of these things. So instead of it looking like the typical profile, it looks a little bit different, but it's the same underlying equations. But what I want to point out here is, let's look up here. So we have our Prandtl-Taylor model tells us there's two regions where we're going to try to fit a velocity profile. And then we look down here, we have our first region down here from 0 to 11.5, right? That's this region here. So we're saying in that region, we have a constant velocity profile. A constant velocity profile plotted in terms of a log plot looks like a log, right? So that's actually linear, but on a log plot, it looks like that. So it's saying it agrees really well, kind of up until, I don't know, inner position of 4 or 5, something like that. And then you get into this middle region here, where it maybe doesn't agree so well. But then in the outer region, as you go further and further away from the wall, it actually starts to agree really well again. And if you think about what's happening there, you have one region where clearly molecular viscosity is the only important thing. That's really close to the wall. So we have a really good agreement there. You have another region where molecular viscosity is not at all important. And it's only the eddy viscosity that's important. And that agrees really well. In this middle region, it doesn't do so well because you have both things that are happening at the same time. They're competing, both effects are important. This is actually called, there's a name for it, it's called the buffer region. And then the buffer region, sometimes you get these models that come back with, here's our equation here for the buffer region. So this von Karman model actually has specifically an equation that's supposed to fit the buffer region a little bit better. You see, Spalding has been optimistic in trying to have a complicated curve fit that matches the whole region at once. Van Driest is same idea, but now it's in terms of du/dy. So there's just different approaches to doing this, but some of them try to deal more explicitly with that buffer region. Let's see, anything else here? Let's look at this slightly confusing plot on the way we're normally accustomed to looking at it. So this is just a plot that shows the same thing we looked at in the previous plot, but it's in terms of not log. It's our conventional way of looking at the data. And you do see that at this interposition, really close to 1, this is where all the velocity gradient is happening, right next to the wall. So you see, yeah, it agrees really well as we're really close to the wall. You start getting a degree of separation between the best fit, the actual solution, and the one we assumed in this buffer region. And then as you get further and further out, it agrees pretty well again. Yeah.
Of those 4 models, the one that's
yeah, that's a good question. I don't have a good answer for that because I haven't personally done a lot of this stuff for myself. So I don't know in practice which one is the best one to use. I would imagine, you probably want to have, what you need to think about is the solution that you're coming up with only trying to get a good estimate of what's happening right at the wall, like in that, really linear region, or are you trying to kind of model what's happening over that full range? So if it's right next to the wall, it's really good accuracy to just use Prandtl-Taylor. If that's all you care about, say you just care about the shear stress right there. So that would be necessary. But if you wanted something that's maybe more comprehensive, then you'd need to go to the more complicated formulation. So, the rule of thumb is you always do the simplest thing you can get away with. So it kind of depends on your situation, but yeah, I suppose somebody who's actually done a lot of modeling in this particular area would have their preferences. So yeah, so this is the velocity profile. Again, you can see how it fits. There is some error, but you do a pretty good job with it. So this is one of the laws of the wall, or a representation of the law of the wall, which is just a velocity profile as a function of interposition.